Hi, I'm Ellie Pinchers, an Education Officer at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our Weather and Climate teaching guide with accompanying classroom resources which can be found on our website, MetLink, with links in the comments below. In this film, I'll be focusing on weather measurements, what and how variables can be measured, and how measurements can be introduced into your teaching. Measuring the weather can be included in your teaching in a very simple, cheap and engaging way, encouraging students to get up and out doing fieldwork, even if it is just outside in the school grounds. Teaching in such a hands-on way, but also in such close proximity to the classroom, should make the subject of weather interesting, but also very relevant to everyone's day-to-day business. Weather observations and data are useful to have for many investigations, helping to understand both physical and human processes. For example, the weather can have effect on people, from what you wear when you wake up in the morning, to changing the responses people give to surveys. With this in mind, what other human behaviours does weather impact? Perhaps travel and sporting activities? Do microclimates impact what we use the land for, and vice versa? All this weather data can be collected in a number of ways. Firstly, primary sources in the form of direct measurements using instruments. These instruments can be anything from homemade or cheaply available instruments to highly precise professional instruments. A second source of weather data is from secondary sources, which is data that's available on the internet, and there is abundance of it on the internet. Professional weather measurements, for example the data collected by the Met Office, are now collated by automatic weather stations. The instrumentation digitally records the measurements and then transmits them back to a central place to be analysed and used. Let's now take a look at the different weather variables which can be measured. Observing clouds can be a very useful way of assessing what's going on in the atmosphere. We can observe both the cloud type and the cloud amount or cover. This figure shows some of the most common cloud types. You can see here that they are categorised by their height and their appearance. You will find our cloud wheel cutouts on our educational page MetLink to use with your students. So how does it help us understand the status of the atmosphere? Let's consider a few examples. If the sky is clear, does it imply that high pressure is dominant over the area? Or perhaps a tropical continental air mass has moved over? If there are cumulus clouds, then there is instability in the atmosphere and convection is occurring where warm air rises. Is this because there's a polar air mass? In a sky where there is stratus cloud, does this imply that a tropical maritime air mass is overhead? A warm front is moving over, or maybe an area of high pressure is causing anticyclonic gloom. In the presence of a cumulonimbus cloud, is this due to the passage of a cold front, or is it just a summer thunderstorm? All of these examples are explained in their corresponding videos later. Cloud amount or cover is recorded in octaves. Octaves are eighths of the sky. If the sky was completely covered in cloud, there would be 8 octaves of cloud, but if only half the sky was covered, it would be 4 octaves. In the event where there's a low-lying mist or fog, the observer will report the sky as obscured. Here we are interested in both the wind speed and the wind direction. We use anemometers to measure the wind speed. With anemometers, you generally get what you pay for. Cup anemometers, like this one here, are the best because they work no matter which way the wind is blowing from. However, they can be expensive and are very delicate. Propeller anemometers can be much cheaper, however a bit more fiddly to use. The propeller has to be pointed into the wind to get a decent reading, and the wind direction can be difficult to work out when the wind is light or gusty. Smartphone anemometers can also be used, and come in either cup type or propeller type. Using the smartphone compass, propeller type anemometers can also give wind direction. However, some smartphone anemometers struggle to record low wind speeds. A cheap and interactive way to measure wind speed is using bubbles. To do this, mark out 5 paces in the direction the bubbles are travelling, which should be roughly 5 metres. Then time how long it takes the bubbles to travel that distance. Divide the distance by the time to get the wind speed. This method is most accurate if the time is measured several times and if the same person is used to mark out the 5 paces each time. With the compass, either a traditional compass or on a smartphone, the wind direction can be recorded. Remember, wind direction is the direction the wind is blowing from, not where the wind is blowing to. So to work out the wind direction, follow a series of those bubbles and measure the bearing back to where you started. Or you could draw a chalk compass on the ground and use this to work out where the bubbles are blowing to and therefore where they're blowing from. There are many other ways of making simple weather vanes to determine wind direction. Wind speed varies with height from the ground. Measurements should therefore be taken at the same height, for example as high as you can reach. Measurements made with a handheld anemometer at about 2 metres above the ground should be increased by 1/3 to get the equivalent 10-metre wind speed, which we learnt from the previous video is a standard height for a wind speed measurement. Where you are taking the measurements also needs to be considered. Buildings and vegetation impact wind speed and direction, and so will have an impact on the microclimate around them. Unless you are specifically investigating the impact of these objects on the wind speed and direction should be measured in an area clear from buildings or vegetation. In addition to this, the Beaufort scale can be used to estimate the wind speed. Different versions of the Beaufort scale exist, over land and over sea. There are a number of thermometers that are available to record the temperature. Digital thermometers are available in many forms and can be very cheap, costing just a few pounds. They are frequently incorporated within other designs such as your mobile phone and smartwatches. However, there are some basic points that remain true of all, with the exception of the most expensive digital thermometers. Number 1. For the thermometer with a probe, be careful not to touch a probe whilst using the device. For those without probes, don't block the air inlet in the thermometer. This will be a very small hole in the plastic casing. Number 2. Most digital thermometers have an accuracy of ±3 degrees Celsius. This means that you can compare measurements made by the same device in different places. However, before comparing the recordings with another thermometer, you will need to compare them in the same place and time at the start. To do this, leave the devices in a dark enclosed space overnight. Record the difference in the reading they show. You will need this difference to adjust readings made down the line. Number 3, digital thermometers do not record new temperatures instantaneously. They do need some time to adjust. You should allow for a minute adjustment time per degree of temperature change. So a thermometer taken from a heated room to outside on a cold day should be given at least 10 minutes to give an accurate temperature reading. Number 4, all thermometers should be shielded from direct sunlight. Traditionally, a Stevenson screen is used. These allow air to flow in but reflect much of the sun's direct sunlight. Placing a digital thermometer in a shaded place is a good start. Number 5, temperature also changes with height, so the temperature at ground will be different to that a metre above the ground. Consistency is key here. Use the same level to make all your measurements. Digital thermometers in cars can be very useful, particularly when looking at urban temperature patterns. The thermometer is usually located within the wheel arch of the car, and so the car should be moving for at least 5 minutes before the temperature is recorded to ensure that air trapped while the car was parked has been replaced. There are a couple of affordable thermometers that can be purchased and used in the classroom. Infrared thermometers like this one here are an affordable, robust and easy to use option. These thermometers allow you to record small scale variations in temperature as they show the temperature to 1 decimal place. They also allow measurements to be taken of distant objects such as clouds. IR thermometers work by measuring the heat from an object. It doesn't matter how close or far away it is, as long as it fills the field of view. Typically this means that an object 10 metres away from the thermometer needs to be 1 metre big to be able to be measured. An object 10 kilometres away needs to be 1 kilometre big. To measure the air temperature using an IR thermometer rather than an object, hold a piece of white paper in the air for a few minutes to allow it to adjust to the local temperature. Then point the thermometer and read the temperature. 21.5. USB data loggers are great to use when collecting data over a few days, for example during microclimate studies. They contain a sensor of temperature and sometimes humidity, processing electronics, and a logger with memory that can store many thousands of readings. They are left to record for days or weeks, then plugged into a USB port and the data downloaded, usually as an Excel spreadsheet and a graph. They can be weatherproofed using small weatherproof containers, allowing them to be left outside for lengthy periods of time. Pressure is a relatively easy weather variable to record, as there are no small-scale variations. The pressure recorded inside a building will be the same as the pressure recorded outside. Many simple instruments, such as digital thermometers and watches, now report pressure as well. Gadgets which display simple weather forecasts, usually as the sun or rainfall symbols, make these forecasts based off pressure changes, equating a falling in pressure with a likelihood of rain. The Firefox app allows phones to be used as pressure logging devices. Although it's possible to make a barometer, either with a liquid in a tube or a simple aneroid type barometer, such instruments invariably respond to temperature changes as well as pressure changes. So that pressure at different weather stations at different heights can be used to draw up a weather map, atmospheric pressure is always quoted as what it would be at mean sea level. Pressure decreases to roughly 1 hectopascal or millibar per 10 metres increase in height, although the actual value of the correction to mean sea level will vary with both air temperature and barometric pressure. To accurately set a barometer, you need to calibrate it to a local Met Office weather station on a calm day. This will have already been corrected to sea level. Once calibrated, you can use your barometer either to record changes in atmospheric pressure if you leave the barometer in the same place, or changes in altitude if you carry it up and down a mountain at a time when the atmospheric pressure isn't changing much. Even simple barometers will record a change in pressure if you move them from ground to the top floor of a school building. I'd suggest trying it with the Firefox app. Humidity was traditionally measured using wet and dry bulb glass thermometers, but these are fragile, cumbersome, and tables are needed to calculate humidity. A cheaper and more practical solution is to use a digital hygrometer. These mainly now come with the thermometers. Rainfall is easy to measure using simple and cheap manual rain gauges, such as this one. The rainfall amount should be recorded at the same time each day and then emptied. To avoid the gauge being blown over by the wind, it should either be placed in a slight hole in the ground or partially buried in a flower pot or similar. However, it is also possible to make your own rain gauge using large fizzy drink bottles. Cut the top 10 centimetres or so off the bottle, invert it and push it back into the remaining bottle. The most accurate way to use such a gauge is in conjunction with a measuring cylinder. Pour any water collected into the cylinder on a daily basis. You will need to account for the aperture of the bottle to convert the millilitres collected into millimetres of rainfall. Automatic, wired and wireless rain gauges can be purchased, either on their own or as part of a weather station, which we will look at in a minute. These work with a tipping bucket, counting the number of times a small bucket fills and tips. These small buckets can usually hold about 0.2 millimetres of rainfall. Similarly to wind measurements, rain gauges should be placed in well-exposed positions away from buildings, walls and trees. All rain gauges should be checked for slugs, spiders' webs, leaves and other debris on a regular basis. Up to now, we've looked at individual weather measurements and the instruments used. However, there are complete wireless electronic weather stations that measure pressure, temperature, wind speed and direction, humidity and rainfall. The measuring instruments, typically mounted on a pole attached to an outbuilding, transmit data to an inside display unit. The data can then be downloaded continuously or in batches. These weather stations are suited to being left in one place, and the data can be analysed to look for changes over time. Cheaper automatic weather stations measure many of the same variables as their more expensive counterparts, but do not generally record information or allow you to upload it to a computer. They usually also suffer from inadequate thermometer shielding, so will be in direct sunshine and overestimate temperatures when the sun is shining. They also tend to underestimate rainfall, particularly during heavy rainfall events. The location of these automatic weather stations is often a compromise between exposure, access and security. A wall-mounted station won't make measurements which are as accurate as a station which is located in an open space. Handheld automatic weather stations record the same range of variables as their larger counterparts except rainfall, with the benefit of being more portable, allowing them to be used in a variety of locations. For accurate wind speed and direction, they should be used in conjunction with a tripod and wind vane. Some models allow for data to be downloaded to a computer, but if using these handheld weather stations, please ensure the pressure has been calibrated as we spoke about earlier. A newer development is the availability of almost complete weather stations that plug into smartphones. These can measure and log temperature, humidity, wind speed and pressure, but again does not capture rainfall data. The accuracy of such devices is at the moment relatively untested. Most countries have networks of weather stations, although there are significant variations in network density. Some countries maintain stations in remote areas such as Antarctica. These observations can often be accessed online. In the next video, we will be looking at weather and climate.